Our interest is to find the probability of error. Here, the receiver is mainly important, how the decision making and based on the receiving signal, the probability of error is getting. So how we require in the receiver two channel correlators. This is one correlator, multiplier and integrator is one of the correlator to get the maximum output. And another correlator, multiplier and integrator is another correlator. So this first correlator, upper correlator, multiplier with phi1, match it to F1. Match it to F1 frequency. And this multiplier with F2, that correlator output is matched with the phi2. So that is how the correlator output X1, the element integrating 0 to TB, multiplying X of t received signal with the phi1 of t dt. Similarly, second correlator output X2, received signal X of t multiplied with phi2 of t dt. So this is what, in addition to the white Gaussian noise for the given transmitted signal vector, so that is how the received signal vector is signal plus noise. Signal plus noise. So we are finding out the correlator output X1, either root EB or 0, whatever it is that we are getting. But here in both the cases, S1, S2, here, this is what, both the cases, this is root EB, this is what root EB, comma 0, and this is 0 root EB. So the correlator output, you are getting either 0 or root EB, and so that here also root EB or here also root EB, or 0, whatever it is. So the decision making, you have to find the difference, which channel output is maximum. Because if binary 1 is transmitted, the upper channel corresponding to F1 frequency gets maximum here, and X1 is greater than X2, where this output frequency F2 is getting minimum output, so that X1 gets higher than X2, because X2 is 0. When our binary 0 is transmitted here, so that X1 is less than, that is 0, and so that X2 gets maximum. So because it is matched to F2 frequency, so F1 correlator output is 0. So that is what the maximum correlator, the matched filter corresponding to the correlator, giving the maximum output based on the orthogonality function. Orthogonality function. So that is where you can see here S1 of t, 2TB, phi1 of t. So here, so the integral output root EB phi1 of t, x of t, s of t is x of t plus w of t multiplied with phi1 of t, phi2 of t dt. So this is becoming 0 because of the orthogonality. We are getting 0 here. Whereas in this case, when S1 is transmitted, okay, root EB phi1 of t, and again phi1 of t multiplied with phi1 of t dt 0 to TB. You will get here this orthogonality gives maximum 1 integral phi1 of t, phi1 of t dt. So that is nothing but root EB. So whenever S1 is transmitted binary 1, you'll get root EB here upper channel and 0 here at lower channel. Similarly, for binary 0, the upper channel output, because this is root EB phi2 of t multiplied with phi1, this is getting 0. Root EB phi2 of t multiplied with phi2 of t, this is getting root EB. Okay, so that is how the difference we need to consider here. See, this is where the correlator output at S1 is transmitted to TB and 0 upper and lower channel, and when S2 is transmitted, upper channel output 0, lower channel output UTB. Because of S2 is phi 2 of T F2 and multiplying with the phi 1 of T at upper as 0, and this phi 2 multiplying with phi 2 in the lower channel, getting maximum. Okay, you understand? So this is how the difference, if you take upper channel is maximum than the greater than the lower channel, the difference is positive. If upper channel is minimum than the lower channel, difference is negative. So that is how either above 0 or below 0 threshold setting to 0. So you can take it as the difference, the output difference x1 minus x2 difference is either y greater than 0 or y less than 0. That is what the decision made. So that is how the probability of error, the detection in the receiver, we decide in favor of S1 or S2, binary 1 or binary 0, if greater than output is greater than 0 or less than 0. Okay, that is how. So now see this is what the decision making 0, the difference y is x1 minus x2. Okay, plus and minus. So threshold is set to 0, chosen as y greater than 0, and it is chosen 1 if y less than 0, it is chosen g. So that is how the FSK is detected, and now the probability of error, whenever the probability of error, we want to find out what is the decision that probability of error, we would like to find the difference of that variance such that the probability density function of a Gaussian random variable of as before, I can take it as probability density function of variable x, okay, or y, whatever it is. Okay, so then see here, let us take of y at whatever it is, 1 by 2 pi sigma square Gaussian distribution. Okay, integral. Okay, this is what minus infinity to plus infinity. Okay, e power minus pi minus mu square 2 sigma square dy, like this. Okay, so this is probability of error is integral function of dik half the equivalent distance to infinity probability density function of, okay, dy. Okay, so this is where this is the function, probability density function. Okay, probability density function, and the probability of error is integrating of the equivalent distance to infinity probability density function over dy. So that is how we just find out the variance. What is the variance here? Sigma square. Sigma square is the variance. Whenever binary 1 is sent, the difference y equal to x1 minus x2. Upper channel output is maximum 2 TB. Lower channel output is 0 when binary 1 is sent. So that is what 2 TB plus. So Whenever 0 is transmitted, the variance, the difference y equal to x1 minus x2. Okay. Upper channel output is 0, lower channel output is root EB. So this is minus root EB. Okay. So that is the output. That is the output at y1 is transmitted, 0 is transmitted. The variance here, we would like to find both the combinations of variances where the two channels are independent, statistically independent. Okay. Sum of these two variances. Sum of these two variances at binary 1 is transmitted and binary 2 is transmitted. So each variance n0 by 2, so this becomes n0 by 2 and n0 by 2, it becomes the variance n0. That is how in the probability density function 1 by 2 pi root sigma square, this is where as I shown 2 pi sigma square and e power minus pi minus mean. This is the S21. Let us take S21 square. That is where, okay, by 2 sigma square. So this is where n0, sigma square is n0. So 2 n0. So S21 is at the binary 0 is sent. So that is how S21 is minus root EB. S21 is minus root EB. So that is how y minus of minus root EB, y plus root EB square by 2 n0. So in this 2 pi sigma square, that becomes 2 pi root n0, 1 by root 2 pi n0. So this is what the major difference we observe compared with the BFSK system. Here, because variance is n0, you are getting 2 pi n0. In case of BFSK, that is Gaussian noise, the variance is taken n0 by 2. That 2 gets cancelled n0 by 2 in BFSK system. In FSK, because of the sum of these variances in the upper and lower channel combination, we are getting n0. So this is the change we observe. Accordingly, the probability of error we can find out so that comparing with the BFSK, what is the effect. So now here the probability when 0 is sent, 1 is received. So that when 0 is sent, upper channel output is greater, then it is treated as decision in favor of 1 because upper channel referred to binary 1. Whenever 0 is sent, if at all you get the upper channel output is maximum, then that is called error. So that is we treated termed as P10. When 0 is sent, the output is greater than 0, that x1 minus x2. X1 is greater, that means upper channel output is maximum. So that is how we integrate the probability density function over dik by 2 to infinity. That is where the threshold L, that is where L x1 minus x2. So you can take it as a 0 to infinity, 0 to infinity. The above threshold where positive or negative, above threshold you are taking as 0, 0, above threshold. Why? That is why it is 0 here. Because the decision making, because of the difference, upper channel is maximum or lower channel is maximum, the decision root EB minus 0 or 0 minus root EB. So that is what plus root EB or minus root EB, the decision boundary is 0. That is why now you take it as 0 to infinity, we would like to integrate. So now 0 to infinity, this function, you can solve it by expressing in the complementary error function. What is the complementary error function of u? Okay. As you know that already we discussed 2 root pi, okay, 2 root pi integral u to infinity e power minus z square dz. This is the complementary error function of u. This is the lower limit. So it's a decreasing function, exponentially decreasing function. We express in terms of complementary error function. So now if you take this part as z square, this is what z square you can take. Then z equal to y plus root EB by root 2 n naught. So this is what z e power minus z square we substitute in terms of e power minus z square. So that becomes z is y plus root EB by root 2 n naught. So then you can take it as dy equal to dz multiplied with root 2. Okay, you can take it. So then you substitute here e power minus z square. Okay, dy is dz into root 2 n naught. This root 2 n naught gets cancelled. So that is how you are getting 1 by root pi integral exponential e power minus z square dz. This lower limit 0 substituted here, y equal to 0 substitute here, root EV by root 2 n naught is the lower limit. So at y equal to 0, so that is what y equal to 0. So lower limit becomes root EV by 2 n naught. So that is why root EV by 2 n naught, that upper limit infinity, y equal to infinity, that becomes infinity. So probability of error when 0 is sent, 1 is received, P10 is equivalent to 1 by root pi integral e power minus z square dz, u to infinity. This is the u, root EV by 2 n naught. You can express the complementary error function as equal to half complementary error function of u root EV by 2 n naught. This is what P10. Similarly, see, this is where we understand P10, half complementary function of root EV by 2 n naught. Similarly, when 1 is sent, 0 is received, you can derive as similar to that. You will get the same equivalent to half complementary error function of root EV by 2 n naught. So averaging of these two binary 1 and binary 0 probability of errors, you will get the average probability of bit error equivalently the same. So this is what probability of error half complementary error function root EV by 2n. You see here root EV by 2n naught. This is the function. This is the function in this complementary error function. If this ratio is more, the probability of error decreases as it is a complementary error function. So this is a exponentially decreasing function. If EV by n naught is more, then probability of error is less. So if EV by n naught is more, then probability of error is less. So that means it's a signal to noise ratio. signal to noise ratio, high signal to noise ratio gets less probability of error. That is obvious. So if this function is small, then probability of error increases. So that is poor signal to noise ratio increases the probability of error. So now if you understand the probability of error comparing with PSK, what is the PSK probability of error? So here, see here, however, that is expressed in terms of Euclidean distance. Euclidean distance, you can substitute Euclidean distance. This is a root 2 EB. So this is the standard equation we derived earlier, dak by 2 root n naught. This is what that is made equal. We got the same. And similarly, comparing with the equivalent distance also, the BPSK and FSK, for example, in BPSK, what is the BPSK? In BPSK, equivalent distance dak is 2 root EV, and in FSK, okay, dak is 2 root EV. See, equivalent distance in PSK is more than the FSK. That is how the probability of error in PSK is less than FSK. Because whichever more highest the equivalent distance gives less probability of error, because it's a complementary error function, decreasing function. This value is large, error is less. So the equivalent distance in PSK is more than the FSK. Obviously, probability of error in PSK is less than an FSK, or probability of error in FSK is more than PSK. Similarly, we observe in the energy, see here in BPSK, the probability of error of BPSK. What is that BPSK? Okay, half complementary error function of we derived earlier root EV by n naught. Root EV by n naught. But in the FSK, half complementary function of root EV 2n naught. So because of the variance added in the upper and lower channel, we got this 2 factor. See here, probability of error in a BPSK is root EV by n naught, which is higher value than the smaller value in FSK, root EV by 2n naught. So that is how the probability of error is less in case of BPSK than FSK. If you want to make the same value of the probability of error like in BPSK, you want double the energy. You want double the energy in FSK. To make equal the probability of error in BPSK, you want to modulate, you want to modulate with the double energy, double power of the than PSK. So that is what to make equal to PSK. So FSK, if you take double the energy, twice that energy or double that energy, which makes equal this probability of error FSK is a same as half complementary error function of root EV by n naught. So that is how, if you want to make equal the probability of error in PSK and FSK, we need double energy or double power to modulate in case of FSK system. So that is how in terms of performance, because probability of error in FSK is higher than PSK. So FSK is poorer than PSK. So which gives the best performance in PSK than FSK. So BPSK is better or superior than BFSK.